A thin rod of length 2L is centered on the x-axis as shown below. Okay, x-axis centered, check. The rod carries a uniformly distributed charge of Q. Okay, so we want to determine the potential V, electric potential, as a function of y, so a distance from the rod, okay, for points along the y-axis. Let V equal 0 at infinity, check. Express your answer in terms of variables L, Q, Y, and appropriate constants, okay? So first thing, we're talking about electric potential, so I'm going to go look at that real quick. So we have electric potential, whoop, whoop. Scroll down slightly. So electric potential is the amount of work needed to move a unit of charge from a reference point, in this case it's going to be infinity, infinity, to a specific point inside the field. And, okay, that makes sense. So the idea with electric potential is we take a point from infinity and we bring it in close. And the amount of work that takes will define the potential. So you'll kind of find that electric potential, I guess potential in general, will be related to work. So you have a relation between potential and work. Kind of like when you're talking about electric fields. When you start talking about electric fields, that'll be related more towards acceleration or force. Okay, focus. So we're looking at a point charge. So right here, electric potential due to a point is 1 over 4 pi epsilon naught Q over R. So that's what we're going to use to get started on this guy. So I'm going to start off with adjust. V is going to be electric potential equals KQ over R, where the K is just 1 over 4 pi epsilon naught, Coulomb's constant, if you will. So we're going to redraw this. First thing you pretty much always do whenever you're solving a problem is you draw it. In this case, I guess we're redrawing it. This is already drawn. Up, there. We're going to, so this will be some distance y. It's a terrible curly bracket. Curly bracket. There we go. I don't think it actually helps to say it, but I like to pretend that it does. This will be r, and then this will be a distance x, and we'll be looking at this portion right here. This portion I'm going to call delta x. Delta x works well. And so the idea is we're going to try and integrate things. Maybe it'd be easier if, yes, maybe. I'm going to adjust the way I'm going to look at this real quick. So, see how back my control Z goes? Yeah, pretty well. So, I'm instead going to look at it in terms of this. So this will be x, and this will be delta x. Just changing what I'm looking at. Totally fine. I think if I do it this way, it might just be easier with how the signs work out. Okay, so now going at this, we're going to rewrite our equation here. So we're going to say a small amount of potential, purple, equals K, small amount of charge, Q, over R. So now we have to define what these K, Q, and R is. So K is just going to be constant, so we know that. Not a big deal. Change in Q, though, so the change in Q, that's going to be related to the size of this small little increment that we're looking at here. So that's going to be, I'm going to call it delta x over 2L. So if we have the entire finite rod, which has a charge total of Q, and that total Q covers 2L. So the conversion factor between a small amount of charge in here and to convert that from the distance to the charge, we're going to use the small amount of charge. I'll do it this way. Delta x over Q over 2L. So to re-explain that, because I kind of flubbed the explanation the first time. So I have a small amount of x, and then we will have Q over 2L. If you want to think about it, Q over 2L is just 1, because for every two length of finite rod we have here, we have one full amount of Q. That's kind of what is stated in the problem here. We have a 2L rod, we have one charge Q evenly distributed. Uniformly? Uniformly. Okay. And so we can use this. And now we need to probably figure out what this R is. R, green. So R in this case is going to be x squared plus y squared square rooted. Just the hypotenuse. The Pythagorean theorem, however you want to say it. So if we look at this here, this right here will be R, the distance from our small random point to the top. Now, the reason I switched where the our small little segment was is because I want to call this point here 0, and this goes in the positive x direction all the way up to L. So now, let's see, we can plug this in. So I'll make a little arrow, plug this in. Ooh, light blue. So a small change in potential, a small discrete amount, a delta if you will equal k q over 2L times delta x, and then we're going to divide by 1 over, okay, we'll multiply by 1 over x squared plus y squared square rooted. Okay, now we don't want the small amount of delta type voltage potential. We want the whole thing. So what we're going to do for that is we're going to integrate. So to do this, I'll say the total voltage will be 2 times 0 to L. So what I'm doing is, just to kind of simplify the math, I am integrating from 0 to the end, and I'm just multiplying by 2 to get both sides. One of the things about potential versus electric fields is the electric fields are a vector. They have magnitude and direction. But with potential, they're all scalars. So sometimes that makes it easier, sometimes it doesn't. But it means that you can add them together without worrying about adding vector components, which can be convenient. And in this case right here, it is. So rewriting this a little bit more, we have k over 2L 1 over x squared plus y squared square rooted delta x. And then cleaning it up one more time, red. So we have the 2's will cancel. The k is a constant, so I can pull it out of the integral. The L is also a constant, pull that out. There's supposed to be a q in there. Did I drop the q? There's a q right there. There'll be a q right there, and we'll still integrate from 0 to L. I know there's a capital L. I'm going to leave it at that. It's fine. 1 over x squared plus y squared square rooted. I'm going to convert this delta x to a dx. I'm basically saying delta x goes from a very small definable amount to an infinitesimally small segment, which then basically means it's going to be written as dx. Now this is a form that we are more familiar with. So your first thought about this is, okay, so now we have this. How do we do this integral? Well, chances are you probably don't know how to do this integral. I'm not sure if I could do this integral. I probably could with practice. Long story short, this has to do with an inverse hyperbolic sine. So you get inverse hyperbolic sine, which you can then convert to a natural log. And after a whole bunch of math, which I'm pretty sure you're not expected to know, nor do you really want to know, you get something along the lines of k, q, l times the quantity natural log of x plus x squared plus y squared, where y is a constant, square rooted, and then this will be evaluated from 0 to L. And then when you evaluate that, you will get k q over L natural log of x plus x squared plus y squared square rooted minus natural log of y. And you could probably move that y under here as well then. So it could probably be, let's see. Yep, I think it could be this too. So it could be this, or it could also be k, oh, sorry, these x's are supposed to be l's at this point. So kq over l, no. Okay, hop, there we go. These are l's, kq over l, move down a little bit, natural log of L plus L squared plus Y squared, whoop, all over Y. There we go. And this, after much ado, will be the final electric potential. Okay, so let's take a review real quick to kind of see what we did, make sure we didn't go too far astray. So the idea here was we wanted to find the electric potential of a finite rod, which sounds pretty easy, and it's actually, you can do this for the electric field, and it's actually a little bit easier because you get kind of lucky with how the electric field vectors cancel out. But here, we have our rod. The point we're going to start with is going to do V equals kq over r, which is for a point charge. We then look at a small portion of the rod as a point charge, which is one of the reasons why they say thin here. When you see thin, what they mean is, since it's thin, this portion is very small. And so when we do delta x is very small, we can approximate that as a point charge. So they're actually intending us to use this point charge approximation, which we then, when we integrate it, this approximation becomes infinitely good, and it actually works. Okay, so we had a point charge. We wrote it in terms of a point charge for a small delta x. Delta v equals k delta q over r. We then defined delta q in terms of the charge of the whole length. We then had to define r in terms of x and y. And then we got ourselves an integral, which is incredibly tough. I kind of glossed over it and said, well, here's the answer. It has to do with inverse hyperbolic sine. And got an answer. And then we got this monstrous equation at the bottom, which we could then use to plug in any given, we could plug in a y, and that would give us the electric potential for a given size of finite rod. So I hope this helped. This is the general way that you would approach this problem, and you approach pretty much any problem like this. And I will see you next time. Thank you much.